Hello everyone, I am Dr. Nitin Kumar Saxena. In this video, we will continue the discussion about the potential field. In our previous lecture, we have seen the different cases for getting the value of potential energy. Now, we will continue it with the topic which is potential energy of a system of two charges in electric in an external field. Okay, so we will discuss that what will be the value of potential when we have two charged particles placed in an external electric field. Let's see. We have two charged particles. Suppose we have two charged particles, say Q1 and say Q2. The distance between these two charged particles is R1, 2, right? And these two charged particles are placed in an electric field, right? So I'm saying, suppose the electric field is something like E, due to which I'm saying the electric field lines are like this. Okay, so if you see the electric field lines are here, that means we have an external electric field and two charged particles are placed in this electric field. So what would be the value of potential energy by keeping these two charged particles? So we will start in a way that you know that we have two charged particles. So initially, suppose there is only electric field, right? The electric field is E, is acting initially, and there is no charge particle. Now what we are doing, we are trying to bring the charge particle from infinity, first first charge particle, and after this charge particle, now again we will try to bring the second charge particle Q2. Okay, so the first case is when I'm saying that okay, the first charge particle, the work done in bringing Q1 will be Q1 multiplied with V1, because what is V1? V1 is the potential developed by this charge particle, and work done is, you know that work done is given by the rate of change of charge. So per unit charge, work done for per unit charge is given by potential. So the work done in bringing Q1 charge particle from infinity will be Q1 V1. Now, after bringing the first charge particle, now for bringing Q2, right? So for bringing Q2, we have to work number one, to bring Q2 from infinity, and second, against the electric, against the Q1 charge electric field. Okay, So what we can see here, we can see that it's okay for bringing the charged particle Q1, there is only one external electric field. So we have to work against the electric field external. But when we are bringing this Q2, then in this case we have to work for two different fields. One field which is produced by external electric field to bring the Q2 from infinite, and second against the Q1 charge electric field. So you see, so you can say, if I'm saying it's a W1, sorry, it's a W1, so and W2 is work done in bringing Q2 charge. So what will be the value? W1 plus W2 means work done to bring Q2 from infinite against external electric field, and number 2 against the Q1 charge electric field. So you see the value of work done against electric field. So you can complete it against external electric field. Okay, so what is its value? Its value will be Q2 B2, right? Q2 B2, sorry, right? And plus this will be Q1 Q2 upon 4 pi epsilon naught or epsilon R1. Q1 Q2, the distance between Q1 Q2 is R1 R2. So Q1 Q2 upon 4 pi epsilon R12. Is it okay? So we can say hence total work done will be stored as potential energy in system. This is okay. So total work done will be stored as potential energy of the system, and if you see the total work done is the sum of W1 and the sum of W2. This is W2. So the total potential energy can be given as, how can you give this? Q1 V1 plus Q2 B2 plus Q1 Q2 upon 4 pi epsilon R12. This is okay. So in this way we can find the overall potential energy of a system of two charge in an external field. I hope this expression is clear to you. How can I get it? So I am reviewing again that if you want to make a system like this is Q1, this is Q2, which are at a distance of R12, and these are placed in an external field E. So how can we get the potential energy for this system? So for this system, the potential energy will be the Q1 multiplied with V1 plus Q2 multiplied with V2, right? And Q1 Q2 upon 4 pi epsilon R12. Is it fine? Okay, so let's see the another topic. The next topic is the next topic. So the next topic is that if we have a dipole which is placed in electric field, so how can we get its potential energy, right? So potential energy of a dipole, potential energy of a dipole in an external electric field. Okay, so what would be the value of potential energy if a dipole is placed in an external electric field? So again, I am drawing the same lines. Suppose I am saying, okay, we have uniform electric field like this. This is uniform electric field, and in this electric field, suppose we have a dipole, right? So for this dipole, the total length from the center, as we have already discussed, that suppose if this is minus q, this is plus q, this is the center point of the dipole. Suppose I am saying this A, this is B, this is O. O means center point. So the total distance is given by normally 2A. So from the center, OA is A and this part is A. So this is your dipole which is placed, suppose I am saying this is placed at an angle of theta with this electric field. So we have an external uniform electric field and a dipole is placed in this uniform electric field at an angle of theta. So let's see how can we find its potential energy. You see here that on this charged particle plus q, you will get a force like this, right? And here you will get a force like this, because this is a negative charge particle, so it have the value of electric field in opposite direction. So value of force in opposite direction to the electric field. While this is a positive charge particle, so it has the force direction same as the direction of electric field. Is it fine? So you see, now because of these two forces, what will happen to this dipole? This force will try to move this point B in this way, while this A point will try to move in this way, right? So two equal and opposite forces are acting on this dipole. So due to these two equal and opposite force, what will happen? At the point O, it will start rotating. Okay, so when it will start rotating, so what will happen? Like this. So what will happen? In case of force in rotational system, you get the value of torque. So this means you will get torque, and the torque is given by, if you have the know the formula of torque is given by force into angular displacement. Right? So you see what will happen here. This is fine. Okay. So if this is okay, the force into displacement. So force into angular displacement. You see what is the value of force here? The QE. If I am saying the electric field is E and the charge is Q, so what is the value of force? QE multiplied with, you see, the angular displacement. What is the angular displacement between these two? So for getting the angular displacement, what you will do, you just see, if I draw like this, okay, so and this angle is theta, so naturally this angle will also be theta, right? And for this theta, you see this will be a height and this will be hypotenuse. So this, suppose I am saying this point C, okay? If I am saying this point is C, so the angular displacement between the charge minus q and the charge plus q will be BC, right? So what will be the value of BC here? You can say QE into, what is the value of BC? Simpler, you have the formula, okay, I am giving here, the sine theta is height upon hypotenuse, right? So the BC is given by AB. What is AB? 2a sine theta. So this means I can write here the value of BC, and what is the value of BC? 2a sine theta. Now you solve this, and how can you solve this? For solving, you see that you have studied that q into 2a is known as P. P is given by q into 2a. This we have studied when I discussed the definition of electric dipole. So this means q into 2a can be written as P. So if I write like this, what I will get? I will get P E sine theta. Okay, so this would be the value of torque. This is fine. So this will be the value of torque. So what we have got? We got that if this electric dipole is placed at an angle theta with this electric field, so or in other words you can say in short, because we know the direction of P is always from minus charge to plus charge, and the direction of electric field is this. So you see here the P and E are at an angle theta. So normally, in other words, we can also say this P cross E. Okay, so if I want to write this formula in vector form, then P sin theta means the cross product of vector P and vector E will give you the value of torque. Right? This is fine. So we have proved what would be the torque on this dipole when it is placed at an angle theta. Now see, if I am saying, now this dipole is at an angle theta, and now I want to shift it for d theta angle. Okay, so obviously if I want to, like, if this is at like this and I want to do like this, so in moving this dipole with some angle, I have to work. Okay, I have to work. So I'm saying, okay. So if I'm saying, like, we have shifted this dipole. We have shifted this dipole for a small angle d theta. Okay, so if I shift this dipole with a small angle of d theta, so for doing this, we have to do some work on it. So we can say the work will be given by the small work to shift it only d theta will be the small work. So this small work will be d theta, right? And if I am saying, okay, I want to move this dipole from angle theta 1 to angle theta 2, So in moving this, the work done will be given by where theta goes from theta 1 to theta 2. This is okay. So in this way, if I integrate from the angle theta 1 to theta 2, I will get the total value of work done on this dipole. So let's solve this. So I'm putting the value of t is Pe sine theta. So if I put the value, okay, let me do here first, then I'll go there. The value is theta 1 to theta 2 for the value of theta. So Pe sine theta d theta. Solve this, then you will get Pe minus cos theta. Okay, so you will get Pe minus cos theta from theta 1 to theta 2. This is fine. So this means Pe cos theta 1 minus cos theta 2, because like the first term will be negative, second term will be positive. So I'm just reversing the terms, and when I will just reverse the terms, then I will get Pe cos theta 1 minus theta 2. This is okay. So this means if I'm saying, okay, this means I'm saying if dipole was initially at angle theta 1, right, and from theta 1 it goes to theta 2. So from theta 1 it goes to theta 2. So for bringing this, or for rotating it, from theta 1 to theta 2, work done on dipole will be Pe cos theta 1 minus theta 2. Okay, so what I am saying initially dipole was at angle theta 1, and from theta 1 it goes to theta 2. So in bringing it from theta 1 to theta 2, we have to do some work, and this work done on dipole is given by the formula Pe cos that we have already derived here, right? And since we know that the work done on any charged particle or the group of charged particle is stored in the form of potential energy in it, so hence potential energy will be Pe, right? So if the dipole initially at theta 1 and finally it moves to theta 2, so in doing this, the potential energy stored in this dipole when it is placed in external electric field E, the work done is given by the formula Pe cos theta 1 minus cos theta 2. I hope this is clear to you. Suppose the special case. What are the special case? You know that if the value of theta 1 is 90, the value of theta 1 is 90, means this dipole is something like this. the dipole is like vertical to the electric field, means this is the electric field, so plus q and minus q. This is the position. So in this position, the angle theta will be 90 degree. And if it is like this, q minus q, so the theta will be 0 degree. If I am saying it's like this, that this is q, this is minus q, means what I am doing, I am like this rotating q like this. So q is coming here and minus q will go here. So in this case, theta will be 180 degree. Okay, so if I am saying, okay, initially the dipole was in this position, so theta 1 is 90, and finally the dipole is in this position, so this position means theta is 0 degree. So what will happen? The potential energy is stored and this dipole will be Pe cos 90 is 0 minus cos 0 1 will be minus Pe. Okay, right? So this means if it is initially it is at this position and finally it comes to the vertical to horizontal position, then the potential energy stored in it is minus P. And if I am saying initially it was at this position, finally it is coming to this position, then what will happen? The potential energy will be Pe cos 0 1 minus cos 90 0. So 1 minus 0. Pe. Okay. So if it moves from horizontal to vertical position, the stored potential energy will be this P, and if it is initially at vertical position and finally it is coming to horizontal position, then its value will be negative, right? So you see, like potential energy is, you see, like if I am saying that, you see here the potential energy is 0. So like the potential energy 0 means the charge particle or the charge system, like here the dipole system, will be in rest. So this means this charge dipole will be in rest when this is kept at vertical, right? Theta is 90 degree. So I hope the concept of potential energy stored in dipole when it is placed in external electric field is clear to you. Now I hope this is enough for this lecture. I'm like finishing this lecture at this point. So in this lecture we have seen that number one, we have seen that yes, what would be the value of potential energy if it is placed in an electric field of two charges. Like when two charges are placed in an external electric field, what would be the value? And finally, how can we find the potential energy of a dipole which is placed in an external field? Thank you very much.